Okay, morning everybody. Let's get going. So what we're going to talk about today is parallel programming. And let me shrink down a couple of these windows. Good enough. Okay, so we're talking about parallel programming because it's an important programming tool, but also because it's really useful for Milestone 4. And let me just adjust my video here a bit. Okay, there we go. So in Milestone 4, you're going to solve this traveling courier problem where you're given depots, pickups, and drop-offs, and you're supposed to find the fastest delivery route. And we already talked in lecture about how you can do this. And one of the key components in what you're going to do is estimating the travel time between all these locations so that you can rapidly try reordering the deliveries and rapidly figure out if you've made the travel time better or worse. Okay, so you got 50 seconds to do this whole thing. So you can get a much better answer if you pre-compute the travel time between all the interesting intersections, places where you have to do deliveries or drop-offs, or the depots where you pick up your truck and leave your truck. So what you're essentially creating is a matrix of delivery times. So from interesting intersection number one, I can get the travel time to all the other interesting intersections. So this would be from intersection K to intersection 1, from intersection 1 to intersection K, and so on. Okay, so I've got basically an all pairs problem. For all these interesting intersections, tell me how long it takes me to get from one of them to the other one. Okay, we talked in lecture that you could estimate the travel times by just using distance, which is fast, but it's not that accurate. It's going to cost you some quality. Your second option was to compute the exact path between these different intersections, which is accurate but is slow. Okay, so one way we could do that, and again we talked about this in lecture, is we could go through for every starting intersection to every destination intersection. We could call our fastest milestone 3's path search, which was the A-star algorithm. And if we have k interesting intersections, so that's the sum of our depots, our pickups, and our drop-offs in a graph that has a total number of nodes or intersections of n, then actually I'm not going to bother with the poll because we kind of did this in class. Well, why don't you type it into the chat? I didn't bother doing setting up a poll right now, but so for this is not the good way we did it in class. Okay, so if you're in class, you're saying, okay, I got this from class. This is not as good. This is if I use an inferior algorithm. I use A star. So for A star, I have to basically have a double loop. I'm going from every source to every destination. So there are k of each of those. And I got a graph with n total intersections. Okay, so in lecture, we saw a better way to do this. We don't have to invoke A star over and over again. But let's say I didn't know how to do that. How long would this take? So k, well, let's work through it. This outer loop is k times. This inner loop is k times. And then what's the complexity of an A star algorithm? Basically the same as Dijkstra's. An A star algorithm is actually somewhat faster than Dijkstra's, but by a constant factor. In the worst case, this algorithm could go through all n intersections and insert them into a priority queue and take them out of a priority queue. Priority queue to insert or remove is log n, and I could do that n times. Okay, so if I work through this whole thing, this would be a k squared n log n algorithm. All right, so that actually for relatively big k's, and for some of the problems we're going to give you, k can be a few hundred. This is going to be too slow. Okay, so k squared n log n. And then we talked in And this could take a lot of time, right? You might not be able to do this for the largest cases we do. It probably just will take too long. So you would actually just fail the 50-second timeout. So I'm not going to do the poll here again because we did this in class. So this is the better way, where we said, okay, what if we use our fancier multi-target or multi-destination Dijkstra's algorithm? Then from some source intersection, it can find the exact path to a whole bunch of different destinations. So we got rid of one entire loop. And same question, what's the complexity? And Taha actually got this one already. Okay, this is what we went over in class. This outer loop is k times. The multi-target Dijkstra is a clever algorithm. It basically doesn't do significantly more work than Dijkstra. It still goes through all the nodes in the graph, n of them, and inserts and removes them in a priority queue, which is log n to put things in a priority queue, take things out of the priority queue. So this whole thing is k and log n. Okay, so it much faster. Okay, so that mostly is a review of what we talked about in lecture. The reason I'm talking about this again, though, is when you want to speed something up, you want to start with a good algorithm. So we're going to talk about parallelism now, but we don't want to go back to a bad algorithm like this. This is much more work, k-squared work, instead of k work. Okay, that's a big factor. So we want to start by getting our algorithm in good shape. But now we've done that. But maybe we need even more speed. How can we get that additional speed? And that's the main topic of what we're talking about in this tutorial, parallel programming. Parallel programming is a big topic, so you can take entire courses on this. We're just going to give you an introduction to what is parallel programming and show you how you can make the path search algorithm parallel in Milestone 4. You don't have to do this. You can complete Milestone 4 without doing that, but if you do this, it will give you more CPU time to play with. Okay, what's a modern processor look like? They're pretty much all multi-core. If you get any laptop processor, cell phone processor, desktop or server processor, anything that's kind of beyond a really, really basic processor that just maybe runs your washing machine. So that might be a single core processor, but anything more powerful is nowadays multi-core. So a multi-core processor is, well, that's exactly what it sounds like. It has multiple cores, essentially processors, and they can all be doing different things, but they all share memory. That's what makes this not just a bunch of independent processors, but a multi-core processor. They're on the same silicon die and they share memory. So the shared memory is important. So every core is executing its own instructions. So it can be running a different part of your program, could even be running different programs, but they all share this common memory space. And this is a big topic. If you want to learn more about how do you build multi-core processors, how do you make them work well, you can take the ECE 552 course, which is about computer architecture, or go to grad school, because this is a topic that goes on for a long time. So far, in at least the programs you've written for courses at U of T, they've all been what's called single-threaded. So that means you're running on one core, and it appears to own all the memory. So it's doing everything. You're running one set of instructions, one instruction after another, and only your thread or your program is changing anything in memory. Okay, so that's what you've done so far. And when you're writing a single-threaded application, you don't really need to worry about is anybody else changing the same memory as you. That question doesn't really make sense. You have one thread of execution, one set of instructions that are going through. So if you didn't change the memory, nobody else changed it. Okay, but now we're going to move on to applications with multiple threads. So a single program that has more than one set of instructions executing at a time. That's what it means to have multiple threads. Okay, so now I've got two cores basically. Each of them is executing a different thread, doing something different, but they're collaborating to complete a single program, and they're working with shared memory. So they can communicate through this shared memory. They could also cause problems for each other through the shared memory. So with a multi-threaded application, you do need to think about what's going on in the shared memory. Okay, and the basic problem is that multiple threads could modify the same variable and in confusing ways. Maybe they modify it at the same time, maybe they modify it in conflicting ways, and that can cause your program to behave very strangely or crash or get the wrong answer. Okay, so how are we going to parallelize? I'm going to show you a simple program that's easy to parallelize. There are multiple ways to write parallel programs. The way we're going to teach you is something called Openmp, which is a relatively simple way to write parallel programs. It basically does a lot of the work for you, which is good. And it's appropriate for programs where you have a lot of data to process and you're trying to divide it across multiple threads. Okay, so let's say I've got a problem where I want to go from 0 to 100 and just take two arrays that each have 100 entries, A and B, add them together and store them in a third array, C, which also has 100 entries. So very simple vector addition. Normally, let me go back one step. So this is a program that, similar to what you've been writing throughout your career at U of T so far. This would run on a single thread, on a single core, and that's what you're used to doing. Now I want to make it go faster. So to make it go faster, I want to make it run on more than one core, use more than one thread. And we can do that pretty simply. So this pragma, so hashtag pragma means this is an instruction to the compiler. It doesn't change essentially what your program is trying. Well, it's an optional instruction to the compiler. If the compiler doesn't understand this instruction, it can ignore it and just compile the program normally. The program will run more slowly, but it will work. So this pragma says Openmp parallel 4. So for a compiler that understands Openmp, and the compiler we're using in the lab does, this tells it the for loop that comes right after me, you can run in parallel. I want you to split it across multiple cores, multiple threads, and try to get it done faster. And again, if a compiler didn't understand this pragma, it would just ignore it. And actually your program would still get the right answer. It would just run more slowly. Okay, so what does this parallel for pragma do? It basically tells the compiler that instead of running all 100 iterations of this loop on a single thread, as it would normally do, it should instead create multiple threads. The machines we have in the undergrad labs have 4 cores, so Openmp knows that. It can ask how many cores are on this computer. It will create 4 threads, and it will give 1/4 of the work to each thread. So it actually splits this loop into 4 pieces, and you see it's basically said for entries 0 to 25, the first thread is going to compute C. For entries 25 to 49, the second thread will compute them, and so on. Okay, so it's divided the loop into 4 pieces, given a piece to each one of the 4 threads. And then it also creates, it makes sure that the program waits until all 4 of those threads have finished their part. So after this for loop, there's what's called a barrier or a join. The 4 threads have to all finish before the program will keep going. So after this for loop, it'll go back to 1 thread, and we won't have that 1 thread keep going until all 4 of these have computed their answer, so that the C vector is completely done. Okay, any questions on that? Does that make sense? So parallel for is actually the probably most useful construct in Openmp. Openmp has multiple pragmas that you can use, but the one that we want for Milestone 4 and the most useful one is parallel for. Take this for loop and split it across multiple threads. When you're done, when all the threads are done, only then can you keep going. All right, so any questions on that, or is it all pretty clear? I'm going to take that silence as clarity in an optimistic way. Okay, so let me show you a quick example program. And let's see. Whoops, let's see. Okay, sorry, my internet is a bit slower, so the lag is kind of messing me up a little bit. Okay, can everybody see this? Okay, thanks. Okay, so this is a simple program. I'm basically defining a vector length, and I've set it to 10,000. In my main program, I declare three vectors, A, B, and C, and they're all constructed to have vector length elements, so 10,000 elements in them. I initialize A and B. Those are my input vectors, so I set them to some random values. And then I'm going to basically use chrono to tell me what time it is. And then I've got this parallel for. Okay, so Openmp parallel for. That means the for loop that comes next, I want to run on multiple threads. And what am I doing in that for loop? Well, I'm just going through the whole vector. So from 0 to the vector length. I'm going to ask how many threads are there. I'm just curious how many threads are running. So I'm going to make this call to Openmp to tell me how many threads are running. Then I compute my output C, my output vector, and I compute it with some multiplication, division, addition operators, modulus operators on my A and B inputs. So I don't really care about the exact computation here. I'm just doing a little bit of work to keep the processor a little more busy. Then I basically check what time is it now, and I print out how much time has elapsed, and I also print out how many threads were used. Okay, so that's all this program does. It's pretty simple. So slightly more complicated, but not much more complicated than the vector addition that I showed you. Okay, so I'm going to build this. Let's see, where am I? Okay, I'm just waiting for this to update. I think I might have to switch to a virtual machine for the next tutorial. We'll see how this goes. Okay, I'm in the wrong directory, so go down there. Okay, so whenever I'm going to do some CPU time measurements. So every time I do that, I want to always make sure I build the release build with optimization. I can't remember what the last build I did was, so I'm going to build the release build to make sure it's up to date. Okay, so I'm going to run that program. And what does it tell me? It tells me that it took 7.4 times 10 to the negative fifth seconds to run, which is not very long. And then it did use 4 threads. Okay, so let me now comment out. I'm going to do a couple things. Maybe this number of threads this call is happening in a loop, so that might slow me down. So I'm going to comment that out. We're going to compile again and run again to see if it changes the speed at all. And there's a warning now, but it doesn't matter. There's a warning because I just commented out some code. Okay, didn't change the time much, okay? But I'm going to leave that off because I want to make sure that my program is fast. And now I'm going to basically turn off the parallel for. So all I have to do is comment out that parallel for, and now this will run serially again. This is one of the nice things about Openmp. To turn on and off multi-threading is not much code. Okay, so I saved that. I'm going to compile this again. Okay, so the time to beat, there's a warning because I haven't bothered getting rid of my threads variable. So let's run this again. Okay, so this gave, let's highlight this. So when I ran it with parallelism on, it was 7.6 times 10 to the negative fifth seconds. Now that I turned parallelism off, it's actually faster, 3.5 times 10 to the negative fifth seconds. So what happened? This parallelism thing does not seem to be a great idea. It's actually ran faster when I turned off Openmp and just used one thread the way you usually do, versus when I actually said run this in parallel. So what's happening? Any idea? How could this be? How could 4 threads be slower than 1 thread? I used all 4 cores, and that was slower than using just 1 core. It's an issue with shared memory. It's a good thought. In this particular program, this is what's called an embarrassingly parallel problem. So basically, every C entry depends on different A and Bs, which means, and these, I can do all of this in parallel. Okay, so I can basically be reading, every thread can read different parts of A and B, compute different parts of C, and there are no conflicts. So there's no actual problem with shared memory. Shared memory can also slow me down, but in this particular case, that's not my problem. Um, because I have what's called an embarrassingly parallel program. I can just tell every thread to go off and work on a different part of the A and B and C vectors, and they'll all happily do things without getting in each other's way. Any other ideas? What do you think's going on? Do you know what it? You haven't studied this yet. You'll study this when you get to operating systems in 3rd year if you take that course. How much work is it to start a thread? Okay, so when a program begins, 1 thread is created to start running the program. When I hit this Openmp parallel for loop, I created 3 more threads. That actually takes a bit of time. The operating system has some work to do. Okay, so what the problem is here is that the cost in time of starting these threads is more than the gain I'm getting from going through this loop faster. So basically, I don't have enough work. In order for parallelism to get me a speed up, I need enough work for it to be worth starting new threads. So let's just try, I'm going to add 3 more zeros here. 1, 2, 3, actually let's add 4 more zeros. Okay, so instead of 10,000 elements in my vectors, I now have 100 million, so much bigger. Okay, so let's save that. And I still have the parallel turned off. Okay, so this is going to be my serial version again. Okay, so I recompile that, and I'm going to run it. And let's see how long this takes. Okay, so that takes longer now. There's more work to do. It takes 0.34 seconds. Okay, and that was without parallelism. Now let's turn on parallelism. Okay, so all I did was uncomment that parallel for. Whoops. Okay, so I'm rebuilding it, and I'm going to rerun it. Okay, and it took less than a tenth, well, less than 0.1. Okay, so we went from 0.34 to 0.09. That's not quite a factor of 4, but it's close. Okay, so if it was a factor of 4, this would be about maybe 0.85 instead it's, or 0.085 instead it's 0.09. So it's very close to a factor of 4, and that makes sense. If I type ls CPU will tell me information about my CPU. Okay, so what does it tell me? It tells me that I have, it says actually this machine has 8 CPUs. It says CPUs 0 to 4 or 0 to 3 are online, and CPUs 4 to 7 are offline. So I actually have 4 CPUs I can use. So it makes sense that I got almost a 4x speed up, not quite. And yeah, so Taha, you're exactly right. The startup of these threads is slower, but the execution itself is faster. I needed enough work for it to be worth the bother. And now that I'm doing 100 million elements in these vectors, I have enough work that creating more threads is beneficial. Does that make sense? And when I typed ls CPU, I can see I've got 4 CPUs working, so it makes sense that I could get almost 4x speed up. That's about the best I could expect. If everything goes perfectly, the 4 cores are not getting in each other's way, I should get, and the threads, the cost of starting the threads has been amortized, then that's what I should get, and that is close to what I did get. You might ask, why are 4 of the CPUs offline? There really are 4 cores in this processor, but each of them can actually run 2 threads at a time with somewhat reduced efficiency. A security issue was found in some Intel processors a few years ago. So for security reasons, that feature is turned off, which means we have 4 cores. We lost the ability for each core to run 2 threads with some gains. So they're basically just 4 core processors. Okay, so let's go back to, let me shrink this down. Okay, so any questions on that? I guess what do we see in that? First, it doesn't take much code to make a for loop parallel. We literally typed 1 line of code. The Openmp figured out that the right number of threads to use was 4 and used 4, so that's good. There is a startup overhead to creating those new threads, so we only want to do this when we've got a fair amount of work to do in some for loop. Okay, and this is just what I talked about. So speed up versus problem size. We start off with a pretty big slowdown. I didn't go all the way down to 1,000, but if we did this with 1,000 elements, our speed up, which is basically how much faster is it? 1 is a tie, greater than 1 means it's sped up, is less than 1. So we slowed the program down a lot with little vectors. If we get up to 1,000,000, we're starting to get some gain, and at 100 million, we're getting gains that are 3.4. I was up to maybe 3.6. So they're getting close to the 4x speed up that we'd hope for. Okay, so you need enough work. Okay, so that was a pretty simple algorithm. Now let's move on to one that is more relevant to you in Milestone 4, making your pathfinding algorithm fast. So we already talked about the algorithm choice, right? We want to use multi-destination Dijkstra because it changed the computational complexity of our whole problem, so that's way better. So if we put some numbers behind what does that mean, if we have 24 deliveries to make, then running an A star algorithm, k squared times, that was our first algorithm idea, takes 32 seconds. And you only have 50 seconds in this problem, so that actually just chewed up a lot of your time, just computing all the paths between the interesting intersections. If we change our algorithm to the multi-target Dijkstra, where we don't have to invoke the algorithm k squared times anymore, we have to just invoke it k times, it gets a lot faster. So it takes a little less than 6 seconds. So we get a big speed up. Almost on this size of problem, it's over 5x. On bigger problems, it's even more speed up. We could parallelize each of these algorithms. So if we made the A star algorithm parallel, we get a pretty good speed up, 3.5x by using 4 cores. So that's good, gets the time down to 9 seconds. And we can parallelize our better algorithm, the multi-target Dijkstra, and that drops it from 5 seconds all the way down to from about 6 seconds to less than 2. Okay, so we get a nice speed up on that. So what's my point by showing you this? You want to do parallelism after you've tuned up your algorithm, right? You can take this iterative A star algorithm and make it parallel, and you can get a reasonable gain. But it's not as good a gain as I would get from actually improving my algorithm. And after I've improved my algorithm, I can still make that better algorithm parallel, which gets me my best overall speed up. So the combination of parallelism and a better algorithm on this particular problem size actually improved my pathfinding speed by a total of 17.5x. So I went from a 32 seconds that was going to be a problem down to less than 2 seconds where it's not much problem at all. So that's something you always want to try to do. Don't make parallelism the first thing you try. Make sure your algorithms, your data structures are good first, then move on to parallel. Okay, so let me move on to doing a demo of how we can parallelize pathfinding. Yeah, let's see. Okay, let me get rid of that. Okay, so I've got, hopefully you can see that. I've got our reference solution here. And in our reference solution for the Milestone 4 problem, one of the things we do is find the exact right paths between all the interesting intersections and store the travel times in a matrix, just like I showed you. So this is showing a little piece of that code. So it's using multi-destination Dijkstra, the better algorithm that I talked about. And we basically have to go from all the interesting intersections, those K intersections. We have to use each one of them in turn as our start location and invoke our multi-destination Dijkstra. Okay, so this is our loop that goes through K interesting intersections. For each of those interesting intersections, we're going to call our multi-destination Dijkstra's algorithm. And you can see we've got a parallel for on top of this. Okay, so we're saying use multiple threads. So you can take this for loop, which is going over a whole bunch of intersections as start locations for a multi-destination Dijkstra, and you can split that for loop across multiple threads. So give some intersections to each thread, and Openmp is smart enough to know that we've got 4 cores on this machine, so it'll split into 4 pieces. So let's start with this. I'm going to basically start off by just commenting that out. So we're turning off parallelism, and I'm going to show you let's see, okay. And I'm going to show you how fast that runs. Okay, so let me build that. And that's interesting. I don't think I saved it. Let's save that. Let's try that again. Okay, so now it's building. And it's building release. So I always want to test my CPU time on the release build. Okay, and I'm going to run just one of the exercise tests. So I'm saying EC297 exercise, milestone 4, run tester, M4 public, easy Toronto. So I know that has about 24 intersections in it. So it's about the problem size that I was just talking about. And I only want to test it. Okay, so I'm going to run this. So it's going to start off by running load map. Okay, so load map's running. And now it started running my traveling courier problem. We've got 25 deliveries to make. And pathfinding. So this is finding the exact path between all of the interesting intersections. So there'll be, we've got 25 deliveries and 2 depots. So it turns out there's 52 interesting intersections. And basically, it's finding all of the travel times, if we follow the street map, between those 52 intersections. And that took it 5.1 seconds. Okay, and then it used that information to go off and try to find a good delivery order and then eventually hook together a travel route. But we don't care about the rest of this. All we care about right now is that it took 5.1 seconds to do the pathfinding. Okay, so let's go back here and uncomment that. I basically just turned parallelism back on. I put in the pragma OMP parallel 4. Let's save that. Let's go back here. Okay, so I'm just going to use the up arrow to go find my last commands. Okay, so I'm going to rebuild that. So remember 5.1 seconds. That was the number, I think, right? Let's go back and see if I can find the number here.
Yeah, it's 5.1.
Let's see. Okay, so my original number was back up here before all this stuff. Well, actually, I think it scrolled off the screen. So let's ignore that. It was 5.1 seconds. Now let's run this again. Okay, so the only thing I changed is that OMP parallel 4. So now we're going to try using all 4 of our threads for that for loop, splitting the work across them. And let's see what happens. Okay, so pathfinding is done in 1.4 seconds. So it went from 5.1 to 1.4, which is about a speed up of 3x. Okay, so we didn't quite get 4x. And 4x is kind of your upper bound. You don't usually get all the way to 4x. 3x is pretty good. And as we go to bigger problem sizes, we can amortize the cost of creating these threads even more. So when we go to our, not our easy test cases, but our hard test cases with more delivery locations, hopefully we'll get even closer to 4x speed up. So does it make sense? So relatively easy to code this. let me go show you. So I'll pause there for a second. Does anybody have any questions on this? Okay, so it looks really easy, but let me go into this function. Okay, so this is our multi-destination Dijkstra algorithm. And let's just go look in this a bit. Find multiple paths from intersections. Okay, so let me go to this one. All right, it's right there. Okay, so I'm not going to go through this code in any detail, but I guess a couple of key things to notice about it is it has this data structure, okay, all paths. In the lecture, this was, actually, let me go make sure I found the right data structure. Okay. Okay, it's got a couple of things here. It has a priority queue, all right? So we've got a priority queue, and we've also got this data structure called all nodes. So all nodes is, in the lecture, I talked about having a node data structure where you stored what's the best time to every node, what's the reaching edge, etc. That's what this is. Okay, so in our reference solution, that's what we called it. It's a big vector, one entry for every node in the solution, and we keep track of the best time, the reaching edge, etc. as we search for every node in the graph or every intersection. And we also have a priority queue. Okay, and our priority queue is where we're storing our wavefront. So two key data structures, and there's a bunch of code down here that uses them to do this multi-destination Dijkstra search. Let me flip over here to at the top of M3. Okay, so let me go and show you. So those are right now. Okay, those are commented out, which is, that's commented out, that's commented out, that's good. Okay, so what I showed you in that routine is those were local variables. Okay, I had this node storage, all nodes, and I had the priority queue, and it was local inside the routine that I was calling from my for loop. And that's actually good because Openmp will, basically every thread gets its own local variables. So when these are local variables, every thread gets its own copy, and that's actually what you want. You want every thread to have its own priority queue. You want every thread to have its own view of what's the best path to every node and so on, because they're all really doing the same problem. They can't actually share data. But let's say I didn't code it that way. Let's say I coded it with a global variable. Okay, so what I just did is I uncommented this line, defined bad parallel global, and basically now my vector that stores what is the minimum travel time to any node, I just made into a global variable. Okay, and let me go back to the line I was at before. Okay, so here's where I was. And basically by changing that to define this local variable, which was good, that stored my best time to every node and my reaching edge to every node, the local variable is now commented out. And instead I've got a global variable. So what does that mean? It means that this routine, when you have multiple threads that are all calling this routine, they're all going to be sharing the same global variable. So if that sounds kind of scary, it should. That's actually not a good thing. So let me rebuild this. And the only thing I've changed, once again, is I've taken out a local variable that was storing my best path to every node and my best time to every node that my path search algorithm needed. And I've replaced it with a global variable. Okay, I've left parallelism on. So if I go back here, well, the Openmp parallel 4 is still there. And I've also copied over from the unit tests that are public this test case, this public, easy, Toronto, Canada. So I just built the unit test configuration in debug mode, and I can run that. And it's going to run that same Toronto easy test case. Okay, so I'm just going to run it to start with. We'll see what happens. Okay, so load map is going through. That seems okay. All right, now it's starting our traveling courier, and we'll see what happens here. It's going to be slower because I'm running in debug mode, not in release. So slower is okay, but it's kind of not looking good right now. This is really slow. So this is taking quite a while. Okay, so I'm now worried that this might be hung. Okay, so I'll give it a few more seconds. But yeah, it looks like it's hung. So I'm going to hit Control C a couple times and stop it. Hopefully I can stop it. All right, so I just stopped it. So that was just running it. Now I'm going to run it through the debugger, and we'll see what happens when we run it through the debugger. Okay, so running the same thing, but I've got a debugger attached to it. I'm going through load map. Okay, and it's not looking so good. I'm going to hit this pause button to see what's going on. Okay, let's see if I can actually get this to pause. Okay, so actually the program in this case it's crashed. Okay, so it got an abort signal, so something has happened that's bad. Uh, and it basically says I've got double free or corruption. Okay, so I've got a memory problem. Something bad has happened, and I can just as usual look in the call stack to see what's happening. So their last few functions are not very clear. This is all memory allocation details, and something bad has happened. Let's see if I can make this a little bigger. Maybe it makes it a bit easier to see. Okay, so basically the last few functions in the call stack don't tell me very much. That's basically just all the memory allocation going wrong. So I need to go back here to something I recognize. So find paths from intersection. So this is my pathfinding algorithm. And it's basically trying to resize that all nodes vector. Okay, and so that resize call went off into some vector code and never came back. It crashed. So memory was corrupted, something bad had happened. Now this resize call was working for me before I changed it to a global variable, and also if I can try a couple things. So one thing I'm going to do is if you go to Window and Debugging Threads, okay. So I now have this Threads window that I just turned on, and it's basically showing me I actually have 4 threads alive. So you haven't seen this in your programs before, but there are 4 threads running here, and I can see where each one of them is. This is the one it showed me before. It's the one that has crashed. Okay, so I can look at its call stack, and remember I was here. I was at this resize line. But I can go look at what the other ones are doing. So let's go look at this one. So this thread, I'm going to go look at its call stack again. I don't recognize the last few functions, so I go down until I get to something I recognize. Let's make this slightly bigger. Okay, so where was it? It was actually trying to call push back on the same vector. So that's kind of a clue. So one thread has crashed when it's trying to resize a vector. Another thread is actually trying to do a pushback on that same vector. So what's happened is these two threads, this is actually quite subtle to debug, but these two threads are trying to access the same data structure. It's a global variable, so they're both actually trying to access the same data. And they're trying to do different things. One is trying to push some data into it, the other is trying to resize it. And it resulted in corrupting memory. And I can go back to my threads and see where are the other ones. Okay, so this one is, let's look at my call stack again. This one was also doing, well, I was looking at a different variable. So I was trying to push back into a different variable. So that probably wasn't a problem. And then let's look at my last one. Look at its call stack. And it was trying to take something out of the priority queue. So debugging multi-threaded programs is harder. You bring up this threads window and you can see where are my different threads. In this case, I can see I've got two threads that are trying to do different things to a single global data structure, my node data structure, and I got memory corruption. And that's the underlying reason. They were both trying to do contradictory things to that data structure. So one of the things you want to do, so I've broken my program on purpose when I basically changed to this using global variables instead of local variables. So that was bad. But let's go back and look at, let's see, right here. Something you can do if you suspect parallelism is causing you a problem is just turn it off. So what I'm going to do now is I'm going to stop this. So I'm going to stop the debugger. I'm going to comment out parallelism. Okay, save that, rebuild. And I'm going to see, does that fix the problem? Because given that I have I have two threads accessing the same global data structure in different ways, and then I get a memory corruption problem, I suspect parallelism is my issue. I just turned off my parallelism. Now I'm going to run it. Okay, I'm not running it through the debugger. I'm just running it, and I want to see what happens. Okay, so load map is going through. Now it's starting my traveling courier problem. First thing it'll do is pathfinding, so hopefully this works this time. It's going to be slower because I'm running the debug build and I turned off parallelism. So it's going to take a little while. And it did work. Okay, so pathfinding was slower. It took me over 14 seconds, but it completed the run, gave me a solution. Okay, so I can actually tell this was parallelism. Now I'm going to turn it back on. And I'm going to go look at my, I'm going to go back here. Okay, so I know that making this node data structure a global variable is bad. And global variables are kind of dangerous with multi-threaded code. You have to make sure it's okay if multiple threads read from a global variable, that's fine, but it's not okay if multiple threads are both writing to the same global variable, or if one is reading from it and another is writing to it. If that's happening, you need to take some additional steps that we'll talk about in lecture. But the best thing is just get rid of global variables that are being both read and written in your parallel code. If you can turn that into local variables instead, then that Openmp parallel 4, every thread gets its own local variables. They will not conflict. That is your best solution. Okay, so I just commented out that bad parallel global. That was my nodes vector. I'm now going to turn on this other bad global variable. So I'm basically now making my priority queue a global variable. So instead of it being a local variable and every thread gets its own copy, I've now made it a global variable. There will only be one priority queue that everybody shares. Let me rebuild this and we're going to see what happens if I do this. I'm getting a bunch of warnings because I just hacked in these changes in the easiest way I could, but that doesn't matter. And now I'm going to run this through the debugger. We'll see what happens. Okay, so again, I've got this unit test, the Toronto easy unit test. So that's what's running. And my load map happened. My traveling courier has started. And so now we'll be trying to find all of these exact travel times using my multi-destination Dijkstra pathfinding algorithm. And it's running in parallel, so it shouldn't take too long. It's a debug build, so it'll take a few seconds, but it shouldn't take a really long time. Okay, and this is taking longer than I would expect. So I'm starting to get worried that something bad has happened. I'm running it in the debugger, which means I can hit this pause button to see where am I. So I'm going to do that. So I hit pause. All of my threads get paused. So I got 4 threads running. They're all got paused. Again, I've used this. I've already opened it up, but you can go window debugging. Window debugging threads to see the threads view. So I'm going to go see where are my threads. Okay, so I've got 4 threads. I'm in a parallel part of my code, and I can go look where are they. Okay, so let's go take a look. Click on the first one, look at the call stack. I'm in my pathfinding algorithm, and I'm actually trying to take something out of the priority queue. So I'm trying to pop something off the priority queue. So that's where my first thread was. My second thread, so I double clicked on it to switch to the second thread, look at its call stack. Where am I? It's actually also trying to pop something out of the priority queue. Okay, let's click on threads again. Look at the third thread. Where is it? I don't recognize any of this, so I'll click on my call stack to see where am I. Let's look at this. It's trying to check if the priority queue is empty. So I got 3 threads that are all trying to do something with the priority queue, 2 trying to pop something out. Okay, get the lowest cost element, 1 checking if it's empty. Let's check what this one is doing. And this last one is doing something else. So it's checking some data in my all nodes array. What's my lowest cost to a node and have I visited it and so on. So, but 3 of my 4 threads are actually trying to access the priority queue. 2 are trying to pop an element off. 1 is checking if it's empty. And no matter how long I run this program, it's not coming back. It's basically hung. And it's hung because I have multiple threads that are trying to read and write from a single priority queue. Again, the priority queue is global, and that's what's causing me to fail. Now, given that I just saw everybody messing with the priority queue, I'm suspicious that my priority queue is broken. So I'm going to leave parallelism on, and I'm basically going to, actually, let's do it the other way. Right now, parallelism is not working. Maybe I'll turn off parallelism again. So I turn off parallelism. I'm going to recompile. And turning off parallelism was easy. Just commented out that OMP parallel 4. I run my program again. And let's see what happens. Okay, so we've loaded the map. We're starting our traveling courier. And hopefully this now works. It'll be slow because I turned off parallelism and it's the debug build. But hopefully my pathfinding works now. And it did. Okay, so pathfinding was slow, took about 16 seconds, but everything worked. Okay, so again, this indicates that my problem is in the parallelism because I turned off parallelism and it worked. By looking at all the threads, I could see that that they were all accessing the priority queue, which makes me nervous about that. As a global variable, that makes me really nervous. So I'm going to comment out this line, change it back to a regular variable, and it's going to work again. Okay, I can turn my parallelism back on. Okay, so if I save this and rebuild it, now it's going to work fine again because I've gone back to local variables for a priority queue and for that node vector. All right, so let's run this, and this should now work fine. Okay, so it did work, and it's faster again. So even in a debug build, it took 5 seconds to do the pathfinding. So that's it for what I'll show you today. This basically just repeats what I said. When we have these shared global variables, so I've got a priority queue, for example, that is a global variable, and I have that being used inside parallel code, multiple threads, we get a problem. Because we've got multiple threads modifying the same global variable. If I change that code to basically just take this global variable and make it a local variable, okay, so it's been pushed down inside this routine, now it's okay because every one of the threads that is executing part of this for loop will get its own copy of the priority queue because it is a local variable in this routine that we're calling. Okay, so this code is good. This code for parallel is bad. And I showed you a few of the ways you can debug them. So first thing, parallel programs are harder to debug fundamentally. So get a serial program working first. If something goes wrong, turn off parallelism, see if it goes away. Because now it tells you that's probably a race condition. A race condition is where you have multiple threads writing or reading. Well, at least one is writing, and then somebody else is reading it, or somebody else is also writing it. So when you have a shared variable, you can get these race conditions where multiple threads are trying to update it at the same time. I showed you how to do this. You can run in the debugger. You can use this threads window to see all the threads. Difficult to debug parallel programs, but if they're accessing a shared variable where they're crashing, then it's likely a problem with that shared variable. There are a couple ways to fix race conditions where you're modifying a shared variable in more than one thread. The best way is what's called privatizing variables. That's what I showed you. Don't use a global, make it a local variable. Everybody gets their own copy, much easier to think about. It's the best answer. There's a keyword that I'll also show in lecture on Friday called OMP, Openmp critical. So that basically forces the threads to negotiate for access to that shared variable. So they all have to wait. Only one of them can get access at a time. That will also fix the problem, but it will slow your program down. So you generally do that only if you really have to. In our case, it was much easier to give everybody their own copy of the wavefront and that node data structure, and it will be faster. OMP critical is mutual exclusion. So Truman's asking, what's the difference between OMP critical and mutual exclusion? There is no difference. OMP basically allows you to just write these compiler pragmas, and it handles the low-level plumbing for you. So it's actually creating C++ 11 threads code. So you could write this with lower level calls if you wanted. OMP lets you write it in sort of a higher level pragma way, but it is creating a mutual exclusion object. That's exactly what happens. Okay, the last thing we saw was that parallelization, Amdahl's law at work. Amdahl's law is basically you can't speed a program up infinitely, even with infinite processors, if there's any serial code. So when you are going to put the work into parallelizing something, you want to think what fraction of the program can actually speed up. And if only half of your program can be parallelized, the other half is fundamentally serial, then no matter how many processors you have, you're only going to get a 2x speed up. If 95% of your program could be parallelized and only 5% is fundamentally serial, then you could get up to 20x. But you want to think about this before you put a whole bunch of work into parallelizing part of your program. How much faster could it get? Okay, so improve your algorithms first. Openmp pragmas are easier to code than directly writing the underlying low-level threading code, which is the other alternative. Openmp will do it for you. We talked about shared state. Privatizing your variables helps you avoid shared state, global variables in particular that can cause bugs. For it to be worthwhile, you need to parallelize significant amounts of work. If it's a little bit of work, then the cost of creating the threads is going to outweigh the gains. And it's hard. Don't underestimate the effort it takes to write and debug parallel programs. So pick things that are easy to parallel, that take a lot of time, so it's worth the effort, and don't do it first, only do it after everything else is working. You don't have to do it for Milestone 4, but if you want a challenge and to learn about this, you can. Okay, those are my final suggestions. Get something simple working for M4 and improve it, just like always for Agile. So get to a legal solution first, then try to make it better. Once you've got something working, work on your algorithm for a while. We talked about ways to get better path travel times, different ways to improve your ordering. Parallelization should be essentially the last thing you try. You don't have to do it. Can be tricky to debug, but it's a challenge that you can take on if you want to learn more about it. Okay, and that's it for today. I think I'm just about out of time for the tutorial, so let me stop recording, and we'll see if there are people who would like me to do it again.